Good morning, folks. Today, I just wanted to add on to what you had learned last day in regards to the quantitative aspects of electrochemical cells. Now, we went over the quantitative relationships. We talked about where they get the values of E naught, and I explained why the E naught would increase or decrease if the concentrations were not at 1 molarity, based upon equilibrium shifts. Now, there is a way to quantify what the voltage will be, more specific than just an increase or decrease. So the increase or decrease in voltage when an ion is not at 1 molarity can be calculated using the Nernst equation. Okay, now this relates back to delta G, or Gibbs free energy. So if we look back to delta G, modifying the equation, what we find is the E cell. Now, notice the difference here is the E of the cell, or the voltage of the cell, is different than the E naught. Now, E naught means that is at standard conditions. Remember, we had talked about what standard conditions are, or standard state. So if it's not at standard state, what happens is we can calculate the voltage of the cell if we take the E naught minus either RT, which is R is the universal gas constant, T is the temperature in kelvins, divided by N, which is the number of electrons transferred, and F is Faraday's constant, times the natural log of Q. Okay, what is Q? Q is, again, the KEQ expression, ratio of products over reactants. Now, you can be given it in this form where you use the natural log, or you can be given the other form where you are given log of base 10. Now, these are both valid in terms of how to calculate the voltage of a cell when it's not at standard conditions. Okay, now, where can you reference this is found on page 849 in your textbook. Now, if you take a look on page 849 in your textbook, what you will see is in section 18.4, you will see a background to how they take a look at the voltage and then how does that relate to delta G? So they give you some examples. And they give you this for standard conditions. Delta G naught is equal to negative N, which is the number of moles. F is the Faraday's constant. And E naught is the voltage at standard conditions. Okay. Now, on bottom of page 851, they give you a sample question of how you can use this formula. Now, if you take a look on page 852, they do talk about the dependence of cell potential on concentration. Okay, now if you take a look on the top of page 853, what they do is they talk about the effects. So they give you a similar question to what I had done in the previous lesson, where the voltage will be greater or less than. But if you take a look on page 854, if you scroll down, they do talk about the Nernst equation. Okay, and notice here in the Nernst equation, they give you the two different forms right here. Okay, depending on which one you use. Okay, and what they do is they give you an example of how you can calculate the voltage of a electrochemical cell when the concentrations are not at 1 molarity. So if you take a look on the bottom of page 854, and then on page 855, they are able to calculate for you what the voltage potentially would be when aluminum and manganese ions are not at 1 molarity. So this can be found on page 855, and then 855 on the bottom to the top of 856. What they do is they give you some examples of how to use the Nernst equation. So a lot of times what they'll be asking you to do is justify whether or not the voltage will be increasing or decreasing if the concentrations were not at 1 molarity. For chemistry 12, all you need to do is talk about equilibrium shifting to the left or to the right. But what you should be able to do is you should be able to quantify how much it shifts by. You should be able to calculate what the voltage is, and you would often need to refer to the Nernst equation. Okay, so that is just a brief summary of the Nernst equation and how it relates to quantifying the changes in the voltage if the conditions are not at 1 molarity. All right, ladies and gentlemen, what I will do is I'll give you some questions from the Nernst equation for you to try out. And that is it for today. Thank you very much. Have a good day. Bye-bye.